Hello everyone. This video is about chapter 2. So section 2.1 measures of change over an interval. So in this section, it's only everything is about an interval. So this one this section talks about three changes. So the first one, change. The second one, percentage change. And the last one is average rate of change. If we are given 2 points, x1, f of x1, x2, f of x2, so the change is just the f of x2 minus f of x1, and graphically is the vertical change between the 2 points, and percentage change is just the so change is the first formula. Percentage change is just the f of x2 minus f of x1 divided by f of x1. Pay attention to the denominator is f of x1, then multiply by 100%. And for the average rate of change, the formula is just the f of x2 minus f of x1 divided by x2 minus x1. So make sure you memorize all the three formulas and the corresponding units. And for the last one, average rate of change divided the change by the length of the interval, so divided by x2 minus x1, and express how quickly a quantity is changing on average over an interval. So the keyword is on average over an interval. So this one is used for an interval, not for a single point. And graphically, this is the slope of the tangent line. Slope of the tangent line, not secant line. This is the tangent line that connects the 2 points. This is the secant line, not the tangent line. A line that connects 2 points. So if we are given 2 points and use a line to connect these 2 points, the slope of that line is actually the slope of the secant line. And that line connects 2 points is called secant line. And for the interpretation, for the three changes, change, percentage change, or average rate of change over an interval. So it must be over an interval. And we have to talk about first one refers to the input interval, and then what refers to the output description for the function, increased or decreased. And then last one, by how much. By how much you have to include the units. And for the three changes, change, percentage change, average rate of change, all three of them must be used for an interval. We cannot use the three changes for a single point. It must be used for an interval. And the corresponding units for change is just the output unit. And for the unit of percentage change, because both of them are output f of x, so the unit is just a percent. And then for the average rate of change is just the output unit per input unit. And then let's see one example. Example 3. Alright, this is example 3. So example 3, we are given a function equation f of t, and the input is just the t. The unit is hours. T is t hours after 7 a.m. So for the first change, it's just the f1 of x2, f of x2 minus f of x1. So in the calculator, we have y1 there. This is our y1, which is the function equation, and the change is just the y1 of 9 point, because this one is a 9.5, and 11 just means 4 hours after 7 a.m. So it's just a 4. So just for the change, first make sure that you have to, for example, if this one is not just the x directly, so you have to change to 4. And this one, this is 4. This is 9.5. And then the answer is negative 4.4. And don't forget the unit. And the next one is about the percentage change. So for the formula, is f of x2 minus f of x1 divided by f of x1 times 100. So you can pay attention to the parentheses. Do not forget this parentheses. Because if you don't have this parentheses, it means this term minus this term. So make sure you have the correct parentheses. And then multiply by 100%. So for the percentage change, it must be like this. This answer is minus 5.774%. For the percentage change, it must be percent. We cannot use the decimal form. And then the last part, you can see here we have two parentheses. So this is the first parenthesis, f of x1 minus f of x2 divided by another parenthesis. So make sure you include the correct parentheses, and the answer is negative 0.8. And the unit is output unit per input unit. This is the output unit. And the input unit is per hour. Then we are done. So let's see one more example, example 4. So example 4. So example 4 is about the interpretation. So for the interpretation, for example, the first one, write a sentence of interpretation for the amount of change between 2004 and 2007. So the first one, just follow the model, then between 2004 and 2007. The output description, revenues, and then because it's positive, so it's increased. It must be increased. Increased then by 850 unit is $1 million. And then the next one is about the percentage change. So everything is the same except for increased by 17.526%. And then similar, the last one is about the average rate of change. We have to use the formula f of x2 minus f of x1 divided by x2 minus x1. So for this one, it's just everything else is the same except for increased by the. For the average rate of change, you have to say increased by an average. Increased by an average of 283.333 million dollars per year. So these are the three interpretations for the three changes. And next, section 2.2, measure of change at a single point. So remember, last section is all the three changes are used for an interval. This section is about a single point instead of an interval. So the first one is the rate of change. The rate of change, or we can say the instantaneous rate of change of a continuous function at a single point. At a single point is given by the slope of the tangent line. So so this one is about a single point x. The rate of change of the single point is actually the slope of the tangent line. So last section is actually the slope. It's the secant line, the line that connects 2 points. But for this one, since we are given only 1 point, so it's about the tangent line. And the notation, the rate of change of the continuous function at a single point x, we use the notation f prime of x. And the unit for the rate of change, or the unit for f prime of x, is just the output unit per input unit. Because the slope of the tangent line, you can see the slope of the tangent line, the unit is just the output unit per input unit. And then this one, the rate of change expresses how quickly a quantity is changing at a single point. So how quickly is actually the keyword for derivative, or for rate of change. The slope of the slope of graph at a point just means the slope of the tangent line to the graph at a single point, at the same point. And then the second change, first we talk about the rate of change that is used for a single point, and then second is about the percentage rate of change. Percentage rate of change at a single point expresses the rate of change at a percent. So the formula is just this is the formula for percentage rate of change, is f prime of a divided by f of a times 100%. And the unit for this measure, the unit of measure for percentage rate of change is actually percent per input unit. So for this one, it's percent per input unit. And the sentence of interpretation for rate of change or for percentage rate of change, the interpretation is just the 4 parts. 1 refers to the single point. What refers to the output description for the function, increase, then increasing or decreasing. So this one, we cannot use increase, the decrease. We have to use increasing or decreasing. Then by how much refers to the rate of change or the corresponding percentage rate of change. The next part, to draw a tangent line, to a graph at a point. So draw a line that goes through that point. So this one shows you, let's see the first one. If the function graph is concave up, and then the tangent line must be below the graph. And then if the function is concave down, then it must be above. So the third case is, if the function has an inflection point, then you have to make sure the tangent line cuts through the graph. That means half of them above, half of them below. If the function is a linear function is just a line. So the tangent line is just the function itself. So for example, let's see, point B is concave up. So the tangent line is just below. For example, point A is also concave down. Is also concave up. So the tangent line is just below. But for the point D, concave down, so the tangent line is above. And then the special point C is an inflection point. So for the tangent line, you have to make sure, all right, it's half of them above, half of them below. So this is the tangent line. And then example B asks you to state the rate of change is positive, negative, or 0. So B and D are just 0. This is trivial. And the C and the E, point C, point E, both of them are positive. And then the only negative is just A. So, and then, for example, let's change the question to compare the steepness of the 5 points, A, B, C, D, E. So for the steepness, and then the other one is about the slope. So for the slope, we have to consider the sign. But for the steepness, we don't have to consider the sign. Let's finish this one. D is point E is concave up, so it should be above or below. So this one. And then for the steepness, let's finish the steepness first. Steepness, we know that B and D actually they're the same because it's not steep. There's no steepness there is no steepness at all. So B and D they're the same. And then the next one, let's compare C and E. So it seems like E is steeper than C. So E is steeper than C. Then A is the steepness. So A. And then what about the slope? The slope, we have to consider the sign. So we have to consider positive and negative. But we know B and D, the slope is just 0. So B and D are the same. And then C and E are positive. But because E is steeper than C, so it's less than C, less than E. And then the only one, point A is negative. So A is the only negative one. Alright, so just remember for the steepness, we don't have to consider the sign. But for the slope, we have to consider the sign. And then next, a good example is just the example 3. Example 3, A, B, C, D. I'm gonna, because I already give you the solutions, so I am not gonna show you the details right here. So, but make sure you know how to solve for this question. And then next, let's go to section 2.3. Section 2.3, rate of change, notation and interpretation. The rate of change of a function at a single point x is also referred to as the derivative of the function f at point x. The notation is f prime of x, and the second notation is d of dx. But they are talking about the same thing. And then for the rate of change, if we are given the input value is just a, then we can just plug in x is a, that is f prime of a. And the other one is just d of dx. We have the extra part, that is x is x equal to a. So it's read as d of dx evaluated at a. And the derivative, the unit for the derivative f prime is just the output unit of f per input unit of f. And for the interpretation for derivative or percentage rate of change, the interpretation is just the for the single point, the output description increasing, decreasing by how much. And then let's compare this table. For the average rate of change and the rate of change, or just the derivative, average rate of change measures how rapidly a quantity changes on average between 2 points. And for the rate of change, it measures how rapidly a quantity is changing at a single point. And this part, graphically, is the slope of the secant line between 2 points. Slope of the secant line. And for the rate of change or derivative, it's just the slope of the tangent line at a single point. And then for the average rate of change, it requires 2 points. It must be an interval. And for the rate of change for the derivative, it just it requires a continuous function at a point that is not a sharp corner and does not have a vertical tangent. So let's see example. Alright, so first, the left page of page 91 of section 2.3. Make sure you memorize all the formulas. The first one, the change, percentage change, average rate of change. So the first three is used for the first three formulas are used for an interval, and the last two are used for a single point. And the unit is just the output unit. Percentage change, the unit is percent. Average rate of change unit is output unit per input unit. The instantaneous rate of change or derivative, the unit is just output unit per input unit. And the last one, the percentage rate of change at a single point A, the formula is f prime of A divided by f of A times 100%, and the unit is percent per input unit, not per output unit, is per input unit. So this is the summary of measures of change. And then let's see example 2. So example 2, this one is the Apple Corporation's annual net sales in trading dollars over an 8-year period. So for the first one, find and interpret the average rate of change between 6 and 9. So 6, this is a 6. 9, this is 9. So the average rate of change between these 2 points is just we use the formula f of x2. So 32.48 minus 13.93 divided by the corresponding 9 minus 6. So we have a 6.183. Unit is output unit per input unit. Output unit is trading dollars. Input unit is year. So trading dollars per year. This is the answer. And for the interpretation is because the it's from year 6 to year 9. So between year 6 and 9, and the output description is Apple Corporation's, is this part. Apple Corporation's annual net sales. So just use it here. Increased by how much? Increased by 6.186, 6.183 trillion dollars per year. So this is the interpretation. And example B, find the slope of the graph at this point. The slope at a single point means the slope of the tangent line. So this is the tangent line. The slope of the tangent line is equals to rate of change. Alright, because this tangent line, we are given 2 points. This is the first point, 6, 13.93, and this is the second point. And also we are given this one. So just use the formula. F of x2 minus f of x1 divided by x2 minus x1. Then we have the slope. So we have to use both notations. The first one s prime of 6, and the second one is d s dt, where t is 6. And so example C, write a sentence of interpretation for the derivative found in part B. So this one just means at the end of year 6, Apple Corporation's annual net sales. That is the output description. This output description were increasing by how much? By 4.51 units trillion dollars per year. And then D, the percentage rate of change is just the f prime of A divided by f of A times 100%. So everything else is the same as this one, except for the last answer is 32.376% per, and the unit, pay attention to the unit, is percent per input unit. Input unit is year, so percent per year. And then make sure you understand how do we get this one. And the next part is section 2.4. Section 2.4, rate of change, numerical limits and non-existence. So for this one, the rate of change or derivative of function at input A is the limit of secant slopes. So for this one, the left side is the derivative, and the right side, if we don't have the limit part, alright, first let's ignore this part. This part means the slope of the tangent line. The slope of a secant line. But if we have the limit, then that means the slope of the tangent line. Graphically, f prime of A is the slope of the tangent line to the graph f of x at input A. So for this one, it should, in this section, you can see several examples about how can we estimate f prime of A by using numerical method. So for this one, graphically, I estimate f prime of 4. This is 0.4. So we know the derivative at 0.4 is actually the slope of the tangent line. So because we are given, you can see the numbers. This one means 1, 1. This one means 2, 2. So you can just estimate it. And then so at 0.4. And then the derivative is about 0.5. So the first one is graphically estimate. You can see you have to draw the tangent line first and then estimate by using the grids. And example B is numerically estimate. So numerically estimate, this shows you the derivative of 2 points is just the f of x minus f of 4 divided by x minus 4. So you can see here we are given this table, and this one 3.99. Actually, in the first column, the value of x approaches 4 from the left side. So the corresponding, this is the slope of the secant line. Just remember, because we don't have the limit here, and this column means the slope of the secant line between different points. The first one just means between 3.9 and 0.4, and the point 4. So that means we have to plug in x equals to 3.9 here, and the answer is let's finish this one. All right, so this instruction shows you how can we get the data directly instead of using the formula one by one. So the first one, we have to make sure y1 is the correct. All right, you can see first one, plug in this equation. y1 is just our function equation. That is 2 multiplied by square root of x. Then our y2 is the slope of the secant line. That is y1 of x minus y1 of 4. So which is right here. y1 of x minus y1 of 4 divided by x minus 4. Divided by x minus 4. So we have 2 parentheses. And then we use the second window table side, return to this one. And then make sure this is the ask. Independent, this is ask, and dependent, this is auto. Then we click on second graph, return the table. So for the table, you have to plug in, you have to type the first column. Then we get y1 and y2 directly. So the 3.9, 3.99, And just remember, the first column means y1. What is y1? So you can see the first column means, for example, the first one means y1 of 3.9. And the second column means, you can see this is the slope of the tangent line. Excuse me, the slope of the secant line. So y2 is the value we are looking for. And similarly, for the second table, we use 4.1, 4.01. So you can see here, y2 and y3. First, let's copy the data to the column. Then the second one. Alright, this one we just use a 3 decimal place. And then finish this part is 0, 0, 1. For 0, 0, 0, 1. And then 0.5, 0.5. So from this table, we can see that the left side limit is about 0.5, and the right side limit is also about 0.5. So we know the limit exists, and the limiting value is just 0.5. So we got this one from the first table, that is 0.5, and this one from the second table, that is 0.5. So the limit exists because the left side limit is the same as the right side limit. Both of them are 0.5. So numerically, this one, because they are the same, just the 0.5. So this is the second method. You can see the first method is the graphically estimate. We just draw a tangent line and then estimate it by hand. And the second one is numerically. Numerically, we have to finish this table to see if the limit exists. And we just use the second window and second graph. And then example 2. Example 2, so this is a good practice, example 2 and example 2e to f. Alright. And this one shows you that we say the derivative of a function exists at a point. The function is said to be differentiable at a point. So if the derivative of function exists for every point whose input is an open interval, the function is differentiable over that open interval. So this one, 3 cases, shows you that the derivative does not exist. The first case is the function is not continuous at point P. Then we say the function is not differentiable at point C. At point P, then the derivative does not exist. And the second case is the function has a sharp corner. So that means the function is not smooth. And the last case is the function is continuous, but the tangent line is vertical. That means the function has a vertical tangent line. And let's see, example 3. Example 3 is a good practice. And next one, example 2.5, section 2.5. Section 2.5 is about rates of change defined over an interval. This one is over an interval. So we have this formula, f prime of x equals to limit equals to this one. So this one, this is called the limit definition of the derivative. Actually, this section shows you the third method to get the derivative. So for example, example 1, if we are given f of x, make sure you know how to get the corresponding f of x plus h. So for example, the first one, this one, x squared, f of x is x squared plus 1. F of x plus h, that means plug in x plus h. X is x plus h, so it's just x plus h squared plus 1. And then next, this one, square, for example, this is x, so take the square root of the inside one, and this time the inside one is x plus h, so it's the square root of x plus h, and the other one is the same, x plus h cube. And make sure you know how to get the example 2. So example 2 shows you the details of how to get the derivative by using the limit definition of the derivative. This is the third method. So make sure you know how to get this one correctly. And do not just show all the steps, show all the details is the best way to get full points. And the next one, after we get this one, so you can see we can get the derivative directly. Just plug in x is -2, so it's just a -8. F prime 1 is just a 4. So for this section is not tough. The only just to make sure you know how to get. Example 2 is enough. And then example 6. So example 6 is a very good example because example 6 shows you all the three methods together. So the first one is graphically estimate the derivative. So that means we at this point 1 we just draw a tangent line, then estimate it by hand. So this is just 2. And the second one is numerically estimate. So we have to use the table. The table is just a 0.99, 0.999, 0.9999. Okay. And this one is similar, 1.01, 1.001, 1.0001. And the corresponding and then similar this one 2.1, 2.01, 2.000. So you can see the left side limit is 2, the right side limit is also 2. So that means the limit exists is just 2. And the last one is the limit definition. So this one is very similar to so make sure you know how to get this one. This one is similar to example 2. Alright, next section, the last section, 2.6. 2.6, rate of change graph. A slope graph of a function or rate of change graph or derivative graph is the graph that results from plotting the slope of the function. If the function is continuous, if the function graph is continuous with no sharp corners or points that would have vertical tangent lines, then the slope graph of the function will be continuous. So and this one shows you the cases that the slope graph will not be continuous at the point. It's very similar to the differentiable. 3 cases that are not differentiable. If the function is not continuous at the point, then the slope graph will not be continuous at the point. So example 1 shows you the details of how to, if we are given the function graph, how can we get the corresponding slope graph. And just read it. If you have any questions, just send me an email. The next box shows you the strategy to try to draw a slope graph. So step number 1, try to find the points has a slope of 0. So that means has a horizontal line. So in the function graph, it is a relative maximum or relative minimum. Then in the slope graph, it is just the x-intercept of the slope graph. And the second one, identify any points on the function graph that the slope does not exist. So the slope does not exist. The slope does not exist at input values that have a sharp corner, discontinuity, or vertical tangent line. So these are the 3 cases that the function are not differentiable. So in the slope graph, so the 3 cases, if you see the 3 cases in the function graph, then in the corresponding slope graph, it must have breaks. And step number 2, examine each interval between x-intercepts or breaks. So if the function is increasing with positive slopes, the slope graph is above. So just means if the function is increasing, then the slope graph is positive. If the function is decreasing, the slope graph is negative. And the last one, we check concavity. If the function is concave up, then the slope graph is increasing. If the function is concave down, then the slope graph is decreasing. And this one says an inflection point is the point where the function is increasing or decreasing the most or the least rapidly. And also this is the point where the slope has so in the function graph, an inflection point just means a relative maximum or relative minimum point in the slope graph. So in this section, we have a lot of examples. So page 108. So example E. Make sure you know how to draw the how to draw the slope graph. And next one is about example 9, example 10, example 9. So it's increasing all the time. So that means the slope graph should be above. And then since we have an inflection point, it must be a break. So this is the derivative. And then similar for example 10. And example 12. Oh, okay. Example 10. Example 9. Example 12. And the last part is about section. It's the last page of this section. So make sure this table is a very important table to help you to find the correct slope graph. If the function has a relative maximum or relative minimum point, then the derivative in the slope graph is just a 0. If the function is increasing or decreasing, then it is just a positive or negative. If this is the direction, this is the concavity. If the function is concave up, then it's increasing. The slope graph is increasing. If the function is concave down, slope graph is decreasing. If the function has an inflection point, then in the slope graph is the relative maximum or relative minimum. And B, C, D, E. So if a function is continuous but not differentiable, because it has a sharp corner, then the slope graph will have a discontinuity. If the function is continuous but not differentiable because it has a vertical tangent line, so the slope graph shows a vertical asymptote, just like this one, because this point we have a vertical tangent line, so you can see here we have a vertical asymptote. And example D, if the function is just not continuous, then the slope graph has a discontinuity. They're the same. And then that's all for chapter 2. So next video we're gonna talk about we're gonna finish the review for chapter 3 and another video for chapter 4. So we're done. Alright, thanks for watching.